Okay, welcome everybody to another of our series of Kickstarter Colloquia. Today we have two different teams presenting, who I will introduce shortly, but to begin with our usual range of reminders. The colloquia are being recorded and the recordings will be posted on YouTube for the benefit of those people who can't join us in person. If you prefer not to be recorded, please keep your camera off during the session. And in the interest of being able to hear the speaker properly, please mute your microphone if you're not actually the one speaking. You are encouraged to post chat questions at any time using the Zoom chat feature, and we will have time for discussion after the talks and at the end of the colloquium. So today we're going to be focusing on stellar astrophysics, and I am delighted to introduce two excellent research teams from transients and variable stars. Our first talk are going to discuss the software that they've developed to simulate and detect faint halo clusters and dwarf galaxies around the Milky Way, in work led by Andrej Pieres and Clara de Paula Moreira, Raslan, Oliveira, Ribeiro, and Rocío Milagros, and my apologies for my terrible pronunciation. Then we'll hear about Andrej Prsa's work on how LSST will enhance our understanding of eclipsing binary stars and how this is impacted by the different survey strategies that are currently under consideration. So a big welcome to all of our speakers, and we'll begin with Adriano's team. I will stop sharing and please take it away.
Okay, I think you can see my screen. Thank you, Rachel, for the introduction. I will talk about Gawa. There is a code to detect Milky Way companions or dwarf galaxies and faint halo clusters in LSST data. Our group is really large, and you can see some of the names here. Well, the institutions we are working on Linea and INCT do E-Universo. Also have collaborators from the Observatório de la Côte d'Azur and the National Laboratory for Science Computation. And sub-institution is Dexo, and the Federal University from Rio. Okay, my topics is at first scientific motivation. I'll talk about the dwarf galaxies and faint halo clusters around the Milky Way. I will make an introduction to the code that we are working, that is Gawa. We want also to make efficiency of this code, and also we want to test in Gawa with simulations that we'll talk about. And in the end, I want to talk about the prospects for near future before the LSS data will be released. Well, the scientific motivation in the last decades, we are witnessing the discovery of a large number of dwarf galaxies and faint halo clusters around the Milky Way. The main surveys that discovering these objects are the Low Longitudinal Sky Survey and the Dark Energy Survey. There are digital surveys. On the left, we can see the confirmed number of dwarf galaxies regarding the year that they were discovered. And on the right, we can see the absolute magnitude in the V-band regarding the half-light radius. And we can see that the recently discovered objects are reaching the brightness of about 21 magnitude per square second. They are really, really faint objects discovered in the neighborhood of the Milky Way. Well, the basic distinction of the dwarf galaxy and faint halo cluster is the dark matter. Basically, the dwarf galaxies are really dominated by dark matter, and the faint halo clusters are dominated by the stellar mass. The dwarf galaxy has the smallest dark matter halos, and they are really critical to understand the evolution of the galaxies. And on the other hand, the faint halo clusters are possible evidence of interactions between the Milky Way and the dwarf galaxies around the Milky Way, mainly the large and small Magellanic Clouds. Anyway, they have a very old stellar populations, and the stars are really very metal poor. Yeah, even the dwarf galaxy has a small spread in ages and metallicity. Well, what is Gawa? Gawa is an acronym for Galactic Archeology Star Cluster Finding using Wavelet maps. This is an adaptation of WASP code that was used to detect clusters of galaxies at distinct redshift in the same way that we want to, that WASP detects galaxy clusters at different redshifts. We want to detect stellar clusters at different distances. And in this figure, we can see the isochronal mask that we are using to read the stellar catalogs and selecting stars that belong to simple stellar population in a specific distance. You can see, for instance, this mask here in cyan to select one of the specific distance that we are using, and in red we have the simulation. We have one simulation of one object in this in a specific distance that is filtered by another isochronal mask. And how does the code work? Well, at first the user sets the configuration file. There is a list of bins in distance, the path for the files. The code splits a footprint map and star catalogs in multiple regions using the Hill-Peak schema. And we call these regions tiles, very similar to what is done in the dark energy survey. They start from the catalog in each tile, and this is are selecting using that mask that I presented in the previous slide. And we are using a very old and metal poor mask for that. The mask is based on an isochron that is downloaded from the Parsec models. The wavelet maps is used to build the stellar density maps, and after that the peaks in these wavelet maps are detected. The candidates are listed to each tile and concatenated in a single list. The candidates are matched to each other, and finally we have a QA for the final list of candidates. Well, how we run the code. Basically, initially we wrote a Jupyter notebook to run this code. We had a few issues, and now we want to submit the code as a Python script in a cluster of computers. We have two available cluster of computers to submit these Python scripts. One is Linea with 15 teraflops and almost 500 cores, and the Santos Dumont supercomputer. There is the largest computer in Brazil with 5.1 petaflops. And it's important to say that we are using this Gawa code along with this WASP code to detect cluster of galaxies as a model to pipelines to run codes using the LSST data and trying to find the best schema to run these codes. What is all the environment to run that, and to run in parallel and to design the codes. A few improvements from the UFF group that worked with us, mainly Daniel Raslan, along with our collaborator Singulani. They present an initial refactoring of the code. They also implement a code profiling to analyze the time that the code was taken in different functions and also identify bottlenecks in the code. Well, they detected that the multi-resolution filter component that is very input-output intensive is taking a key role into the in the code, given the time span. One of the goals is performing an analysis for the code given the parallelization. Along with Singulani, they implemented a parallelization based on parcel. There is a Python package to run codes in parallel and also in Desk. Parcel is really easy to implement in the code, and Desk is a bit difficult to implement, given that many arrays must be changed to Desk arrays. They have to change a large number of NumPy arrays into Desk arrays to run the code. And basically the conclusion so far are the improvements is basically about 10% when executing in the Santos Dumont supercomputer. They apply a Desk, but not with a large performance gains, and also that the fact that Desk is recommended for projects that are being developed or developed from scratch, given there is a relatively large change or a large time to implement this this package along with the code. Along with UFF, Dexo, the group of Dexo is also working, but working with WASP instead of Gawa. Here is a flowchart written by Rocío about the code, and we can see that basically the code run the detection in a tile, and after I slice, this part is running in parallel and this part is running sequentially. After that, the results are concatenated and the probability of membership of each galaxy to belong to a cluster is calculated, and after concatenate all the results, the code reaches the end. This code is very similar to Gawa code that detects that work with stars, and we want to use these improvements also for Gawa. Here we have the results using different number of slices for one of the functions, and we can see that basically with 20 slices or 20 different beams in distance, the code takes about 50 seconds to detect the clusters of galaxies. Okay, I don't have a lot of time, so I will jump to other slides only to show a few interesting results. In order to measure the efficiency of the Gawa code, we developed a code to simulate stellar clusters. So the simulation is based on a single stellar populations. Based on parsec models, we started to use with the dark energy survey, and now we are using data from the photometric system for LSST, and the code basically reads the catalog of stars, take the stellar clusters, and incorporate it in the same catalog. So we are now basically running simulations with different regions running the QA for simulations to check if everything is good, and running Gawa to detect the clusters, and finally analyzing the results. On the right, I have one of the simulations showing the absolute magnitude versus the half-light radius. We can see the red circles here, they are linked to darker circle here or dark dot here. The difference is that the red points are not filtered by the crowding of stars. We implemented a filter to simulate the observational bias. That is when the pipeline that detects stars is not able to detect all the stars, mainly in the crowded fields. So there is a decrease in the absolute magnitude. And here also I'm showing the absolute magnitude versus the half-light radii comparing to real objects. The globular clusters as X in black and the dwarf galaxies in blue. Here is a basic flowchart about the simulations. There is a main file with all the settings for the array and deck limits and limits in magnitude and color, surveil, etc., and a set of settings for the clusters. So the code basically reads the coordinates and magnitudes of the stars corrected by extinction and populate fields that are not sampling the zero in the case that we are simulating LSST fields. The position of the stars are randomized and a file with a list of simulated clusters is created. The clusters are populated, or the stars in the clusters are set after we download the most updated parsed isochron. The stars from the field and from the star clusters are joined, and we are removing stars closer than a minimum distance. After this, the catalog is exported along with the footprint map to be detected by the Gawa code. And the file with the features of the clusters is updated with the absolute magnitude of the stars, given the most of the stars were removed. The star cluster, as I said, the star cluster is simulated with minimum and maximum absolute magnitude, half-light radius, and distance. And also we are varying the ellipticity and positional angle. We are using group initial mass function, photometric errors from the feet of the P0 stars. We are using a binary fraction set by the user, and only exponential stellar density profiles, and the stars are removed in crowded fields if they are very close to a specific distance, and if they are affected by stellar completeness with parameters fit by the user in the input file. We are avoiding simulated clusters close to the border of the simulations, and the simulations itself is a crucial step to estimate the efficiency of the code, as I said before. And we are still using a stellar density flat because we are reproducing, or we are populating stars outside of the DP0 footprint with stars from DP0. So the density of stars is flat all over the sky. Here is one example of removing stars that are very close to each other. This field is basically 1 arcminute per 1 arcminute. This is one cluster that is simulated, but the stars, all the stars are here, not still filtered. And on the right, we can see that if you remove stars very close to each other, most of the stars will be removed. and the detections using Gawa is done for this cluster. Also, we are making a lot of plots, including the Hess diagrams or the color magnitude diagrams for all the clusters simulated. Here you can see all the stars here, only the background stars in a pixel with basically one square degree. And here I show the Hess diagram for only for the cluster that is simulated. Here is one of the results of the detections for one simulation with 237 clusters. The panels show the half-light radius versus the absolute magnitude in different beams of distance modulus. Here we can see some of the real objects in this beam of distance, but in this case we are simulating only in this beam of distance between 100 kiloparsec and 1 megaparsec, and the beam with the largest number of simulated clusters has 8 clusters. Most of them are sampling 1 or 2 clusters. On the right, I see the completeness of the detections after we attempt to detect the clusters using Gawa. And we can see that for most of the beams, we have a completeness close to 1, or we are detecting most of the clusters, or all of the clusters, but in some cases where we are still working, we have something like 50 or even less in terms of completeness. Here is one of the work done by the students founded by Heising-Simons Foundation. We were testing the simulations because we want to check if the size of the clusters and distance and etc. was really simulated as the input table. So we use an MCMC code to fit the parameters of the simulated clusters. In the plot on the left, we have the true exponential radius of the clusters and the best fitting using this MCMC approach. And you can see that for a cluster simulated between 18 and 120 stars, we can recover the exponential radius very well. We see for the ellipticity a large error, but that is expected since we simulated clusters with ellipticity between 0 and 0.2, or very rounded objects. And also we are able to set the center of the clusters very well. We can see here the shift from the real center, and you can see that most of the fittings are between 0.05 arc minutes. There is 3 arc seconds. That was done by the students along with the plots for completeness and purity, that they worked very hard on that. Well, so the codes about the simulations and the detections, all of these codes are stored in GitHub repositories. We have example of Jupyter notebooks for simulations and detections. The QA is basically an HTML using those Jupyter notebooks. As I said, currently working, we have people from Linear working on this, including me. The Code Azul Observatory, the group from UFF, Dexo, that have weekly meetings, and extrapolating only to having an idea that of time that we are working for LSST, the scale, extrapolating the simulations that we run is about 20 hours to run on LSST scale area. Even we don't have a simulation as large as LSST. But this is one of the prospects that we are working on, to sample the completeness, simulating something like 100,000 clusters, and so populating all the space of absolute magnitude and half-light radius and distance. We also want to download the second release of the simulations for LSST, for the simulations of the Milky Way stars from their lab. And also we want to check if this is feasible to download this simulation and insert it in the code of the simulations and try to recover with Gawa. We are summarizing a complete distinction of all the steps in the simulations that are detected in the paper to be published later. And currently we are finishing a report about conclusions taking advance of all these people working with these codes. And of course, we want to be ready for early science with LSST. We want to be ready to gather the low-hanging fruits of the first data sets. Okay, thank you. Sorry if I took a bit longer.
No trouble at all. It was well worth it for a fascinating talk. Thank you very much. And congratulations to everybody in your group who's contributed to a huge body of work. So I see there was a comment from Andrej in the chat that may have been answered in the talk. Andrej, if you could just repeat the question for the benefit of the recording.
It was, yeah. So I was wondering when you were discussing calibrating, testing Gawa, I was curious about how accurate the stellar cluster simulations were, but then you had a whole slide devoted to it, so that answered itself.
I had a question on the technical side, actually, if I may. I have heard of Dask and Parcel, but I've not had a chance to actually play around with them. How invasive was it to convert your code over to using Dask arrays, for example?
Yeah, who worked more with that is Raslan, but basically the code of Gawa was written by Benoit firstly, and Raslan was the person that wants to implement that, and it was really hard to do that because all of the NumPy arrays were converted to Dask arrays, and we had to test, and we faced a lot of bugs to really get to run the code.
And what is different about Dask arrays versus standard NumPy arrays? How are they structured differently?
I think the structure is different. Raslan is not here, I think. Well, we want to say, I'm not sure. No, but
Adriano,
here.
I'm here, Daniel.
Hi, Daniel. Could you clarify this point?
I can answer that. The organization of the chunks in the array is different. So we have to adapt the organization of the original NumPy array for the Dask array and retest everything to check if the output is okay, the output is the same of the previous version.
Right. So that I can see how that would be a very invasive change in any existing code, as you said.
Yeah.
So unless you're developing it from scratch with Dask in mind, that's going to be a challenge. Okay. Well, that just means your overall workload has been even more impressive because that was quite an effort to update that code. But it's interesting that it's proved a valuable thing to do. Okay, well, if there are no further questions, thank you, Adriano, and your team very much once again. And we will move on to our second talk of today, which is from Andrej.
Thank you, Rachel. Thanks for inviting me. Thanks for lending an ear to see what we've been doing. So let me first share into a chat. I have a bunch of links to share if anybody wants to follow along. So I just posted in chat the links to the slides, to the tarball, if you wanted to reproduce any of what I'm about to show, the IPython notebook that we'll be going through, and then the paper draft, if anybody's interested in contributing to it. All right, so let me start. Here we go. Can you guys see my screen?
Yes, we do.
Perfect. All right. So I'm dropping this here just if anybody wants to take a quick flash of the QR code instead of typing this. But for those online, it's probably easier to just click on the links that I've just shared. So my idea today isn't to educate you on eclipsing binaries and why they're important. I imagine most people know what the relevance is. If not, please feel free to ask me. Instead, what I want to talk about is what LSST will do, and specifically what the proposed OPSIMs that we've been dealing with, the 2.99, bring in terms of novelties, and whether it's worth considering one over the other. So let me start with giving you an overview first of what the simulation's doing. So when we look at all the eclipsing binary surveys out there, they're either localized or they are preferentially of the northern sky. And the only one that's at least roughly similar to what LSST will be doing in terms of the footprint, even though much, much, much brighter, is TESS. So TESS is a planet hunting mission, but it still provided us with a representative sample from the short cadence data of roughly 4,600 sources that we can analyze. And the idea is to grab an OPSIM run, and knowing where those TESS EB sources are, we know the RA and the DAC. So out of the 2 million field visits that we have coming out of OPSIM, we can generate LSST time series for these eclipsing binaries. So we know already what the periods are. We know everything about them that there is to know. So easily enough, we can calculate everything that we need. And of course, we have all the information on the passbands that will be observed in over the course of the mission lifetime, the 10 years. And once we have the time series, the idea is just to count them. So count the number of field visits per passband and cumulatively for each eclipsing binary out there, and see how many we'll be able to get. And then based on this light curve coverage, we can evaluate the probability that we detect this as an EB. So this is, of course, the highest level overview of how we want to approach these things. And we are trying to answer 3 questions. So the first question is it worth it? Do we even want to bother with LSST if we want to do eclipsing binaries, or are we better off just diving into Kepler and TESS data and wait for Plato and so on? Or will LSST do something fundamentally important for us? The second question is whether we have adequate passband visits to provide chromatic information for eclipsing binaries. So there's a lot of information encoded in this question, but ultimately the shape of a light curve will depend on the passband that we're observing in, because of the effective temperature ratio of the two stars that eclipse one another. And so in consequence, we want to know whether we have enough passband resolution, if you will, to be able to say something about the effective temperatures. Because if we don't, then we'll be stuck with what we're stuck with, Kepler and TESS, and that's essentially white light information that gives us temperature ratios, but, or better yet, surface brightness ratios, but not really effective temperatures. So if there is enough passband resolution for us to get individual temperatures, that's going to be a huge plus, because there's no other mission that can achieve that beyond, say, Gaia, once we get the RP and BP passbands. And then the final question is that of comparing different OPSIMs and communicating this back to the SCOC team. Is there a significant difference from one OPSIM to another that would either favorably or adversely affect eclipsing binary deliverables? So the way I figured I'd do this is just show you the worked out notebook. So let me just click on this. And again, this, I'm trying to deviate from the typical talk style of giving this colloquium, and I would appreciate any and all interruptions during this presentation. So I'm deliberately trying to make this less formal so that you guys can jump in with any ideas or suggestions or criticism, so that we can work out any questions as they come. So please feel free to stop me at any point. So we start with this high-level overview applied to the 2.1 baseline computation. This is what we have in effect right now. And based on this, we have the 3.0 coming by the end of the year, where we'll have tweaks of the 2.1 that hopefully affect, so that do not adversely affect the main science goals of the survey, but they may benefit auxiliary science goals that that other people are interested in. So we wanted to see what the baseline is and then compare it to everything else. What you're seeing here, you can, if you download the tarball, you can run this for yourselves. I included all the pertinent files in there, so you can recreate every single number that's in the paper. I'll just guide you through roughly what it is. So of the important things is you load the OPSIM data. OPSIM data is distributed as a SQL database. So what you do is here, just for generality, I define the subdirectory it's in and the suffix, and then I load it up. Once I load it up, we can query all the right ascensions and declinations of all 2 million fields that we have. So here you just select arrays and decks of the fields from all the observations, and here I just want to see how many we have, and you see that you have a little over 2 million field visits. And if you plot the histograms of right ascension and declination, what you want to see is the distribution that is reasonable. So you see that the base distribution is, of course, normal. The peaks, note the log scale, of course. So the peaks that you're seeing here, these are your deep drilling fields. Otherwise, this is the wide fast deep field. And so the right ascension distribution and the declination distribution is precisely what you would expect. So again, here, these little peaks here, those correspond to the deep drilling fields, where the number of visits goes up by a factor of 20 or more sometimes. So this is the first part, getting the OPSIM in. The next thing is to get the TESS-EB catalog in. The way you can do this is you can go to the catalog homepage and just dump the latest version if you want the latest version, or you can grab the CSV file that I used in this case. And from here, what you want to pull is spatial position, ephemerides, because you want the orbital period and the ability to phase the data, and then eclipse parameters so that you know where the primary and the secondary eclipse are. And I'll get back to that point in just a little bit, because it's important for our ability to gauge whether we'll detect an eclipse or not. So then we put the two together. So for each eclipsing binary in the test catalog, we query the LSST field visits. And this is what this block here does. And so as you run through this, you're going to get this variable here that's called EBVRO observations, which is essentially a list that I'm showing you here, what it looks like. So this is the test input catalog ID. And each of the test input catalog IDs has the timestamp here and the passband it's in. And so this is, if I expand this, you see that this particular target is going to be observed quite a few times. So, and remember, this is over the course of the full 10 years. And then, because we know what the passbands are, we can sort this out into the number of visits per passband. And the blog that you're seeing here is just doing that kind of paperwork to make sure that we count all these passbands accordingly. And if we count all of these, it's easy enough for us to plot them. And this is what I'm showing you here. So on the y-axis, I'm showing you the number of EBs. And on the x-axis, it's the fraction of visits for those EBs as a function of passband. And the main takeaway here is that if you're looking at the left-hand side, these are the blue bands, U and G, and they're getting around, say, between 5 and 10% coverage, whereas the red bands over here are getting between 15 and 25% coverage. And the fact that we're getting these 15 to 25% means that for eclipsing binary needs, we are covered. We'll be able to retrieve temperature information on individual components simply because there is enough passband information that each individual light curve will be truly chromatically sampled. And because of that, we'll have handles that few other surveys really have. So going onwards, this is per passband. Of course, we can put this in a quantified form, and I've included this in the paper as well, so that people are aware of what's the fraction for each passband. But remember that this is averaged over every single eclipsing binary out there, irrespective of the number of visits. So the error bars here are really purely qualitative, because as you can see here immediately, these distributions are nowhere near Gaussian. So we report them here only as a figure of merit, so to speak, so that you know what the uncertainty is. But ultimately, though, the mean is what you're mostly interested in. All right, so that's the first part. The second part is to try to assess light curve coverage. And the idea of light curve coverage is to go from time space to phase space. From TESS EB catalog, we know all the periods, so we can go from time to phase. And then we want to create sort of a merit function that will tell us whether this eclipsing binary had been observed in a way that, had we not known it was an eclipsing binary, we'd be able to recognize that it was. And the idea here is, sure, we can simulate the data, we can come up with a set of the period finders or any such algorithms that we'd try out and see if they'd get recognized. But I would argue that that's not the best way to go about. First of all these period finders are very finicky, and we have 10 years to work on them, which means that what we have today is certainly not going to be state of the art in 10 years' time. So instead, I'm proposing something else. I'm proposing to simply count how many points we have in eclipse. And that's what this logic here is. It it seems overly complicated, but that's just because of the phase wrapping. It simply still counts all the number of points within the eclipse. Either primary or secondary eclipse, or both. And what we want to do is simply look at the distribution. So we count them, which is this next part over here. And as we count them, we can then plot the histograms and see what they do. While at it, these counts here will count across the sky. So just to give you an example of how nicely that works, you can say, well, let's ask a question. How many eclipsing binaries will have counts above the number of 1,000? So this is what you're doing here. You say, okay, tell me what are the tick numbers where the number of total aggregate counts is over 1,000, because no WTF wide deep fast will ever be above 1,000. So everything that's above 1,000 is going to be deep drilling fields. And this is our list. So we get these tick numbers over here, and it tells us how many observations, where you see, for example, it can be as large as, say, 20,000 observations that we get there. But we are, of course, interested more in a distribution. So this is what I'm showing you here. So this is the overall distribution of the number of field visits, and this might be the most unexpected result for me. I wasn't aware that the distribution of field visits across the sky, across the southern sky, the LSST footprint, is essentially uniform, more or less uniform in the number of field visits. And because of that, if you are at this region of the parameter space, you're going to be quite well covered. But if you're in this region of the parameter space, there's a slim chance that you will recover the traces of the nature of a system as an eclipsing binary. So this is, of course, every single EB. The more interesting thing for us would be how many visits will we have that coincide with eclipses, because that's where most of the signal will be. And that's what I'm showing you here. So this is the number of field visits during eclipse. Notice that we went up to 1,000 here, and I'm going only to about 500 here. So obviously, we lose any ability to get many eclipses because we run out of eclipse no matter what. But what is concerning is that the peak on the left is the highest, which means you're not going to hit an eclipse for the majority of the EBs. Of course, when integrating this whole thing, you still get a substantial mass, and I'll show you this in just a moment. But ultimately, the fact that you're so heavily biased to the left is working against your science. And the best thing to do at this point is to take this and divide it by that. So it'll tell you what is the fraction of visits during eclipse with respect to all visits. And that's this. So it still tells you that you will have most systems that fall short, that you will not have any in eclipse points out of the entire phase light curve. But then you still will get quite a substantial number in this part where you can do some serious science. And the more to the right you go, the better it gets. But of course, everyone who's been thinking about this should say, well, Andrej, come on, stop, because obviously this has to be a function of the orbital period, right? Because this part over here, these have to be short period binaries where eclipses are super wide. And that's why you're getting, say, 50% of all points being inside of an eclipse of one or the other. And of course, these are contact systems or semi-detached systems, and these are going to be easy for LSST to get. But these well-detached systems on this side is, of course, where we'll be losing it. And just to give you an idea, and this is the metric that I'm proposing, is the following. We're certainly losing these guys over here. We are probably losing these guys over here. So if we say, let's say an ad hoc number of, let's say 0.05, 5%, that we require that there be at least 5% of points inside of an eclipse. If that is the case, then we should be able to recover the nature of an eclipsing binary to a certain, hopefully with certain probability. So if I take this 5% as an example, I can simply say, okay, TESS will observe of all TESS targets, because 4600 are strewn all across the southern and northern hemisphere. There's going to be 2600 systems that will be observed. And of those, we'll have 1683 that'll have at least 5% of the points in eclipse, which corresponds to about 65%. So if this is the case, if say 5% were adequate for us to get that out, then in that case, we'd be able to recover about 65% of the entire sample from TESS. And just to show you this period dependency, so the blue is the distribution that you've just seen from before, and in this orange, I'm showing you the distribution of EBs that have at least 5% of data points in eclipse. And this is precisely what I told you implicitly. So for as long as we're a short period, we're going to recover the vast majority of them. But as we go towards longer and longer periods, this is the part of the parameter space that we're losing, and there's no way for us to recover it with the cadence that we have with LSST. But this, of course, is going to be a gold mine for short period binaries up to around 30 days. Now, I said 5%. This is a completely ad hoc number. So I'm showing you here the situation if I change this 5%. So 5%, you're essentially looking at 5% and you're at this 65% mark. If I wanted 10%, 10% would, for example, be a little under 50%. If I wanted 20% of points to be inside of an eclipse, we're down to 25% and so on. So if you wanted to complicate your merit function, you could by employing this here to say how many points in eclipse we need. If it's a short period binary, it's only a handful because the flux changes anyway at all times. But if you wanted to get it for a well-detached binary, then you really have to get those in eclipse points simply because out of eclipse region of the light curve is completely flat. So if you wanted to run this, for example, 2.5, 5, and 10%, you're getting these numbers. So 76%, 65%, or 46% of recovery. Then I wanted to see, okay, let's just visualize what this looks like. And I'll show you that in a paper, but here, this is the computation of all of those things. And then finally, this is just an example of a deep drilling field of what it looks like. Blue points are TESS, and red points are what the deep drilling LSST will do for you. So it's pretty awesome. And then same thing, only in different passbands. And then this is the part where I just run the comparison with all the other OPSIM runs. The logic is identical to what I've been talking about. So everything that you're seeing concatenated in this cell is precisely what I've been showing you up there. And what it tells you is for this particular OPSIM, this number of field visits, fractions, yada, yada. So all these numbers that I've been showing you before for 1, 2, 3, 4 visits. So if you ever wanted to play with this, this should be a fully functional notebook that you can run on your own. Now, I want to show you, actually, let me do it this way. It'll be easier. So this is the current draft. I'm just going to scroll to the tables, so you'll recognize all the contents because it's just taken from there. So bad news, this one will be missed. Okay news, we may get this one. This one's trivial, and this one's test level. So you can see that LSST will vary widely in what it'll provide for us. The first comparison is what do we get? So these are the numbers that I've shown you. So 2.55 and 10% threshold. If any of these OPSIMs were significantly different from this, that would mean a red flag. But as you can see, all these numbers are essentially within a single percent, which means that for eclipsing binary science, there will be no adverse nor beneficial impact from any of these variations, which means thumbs up as far as we're concerned for any modification that might benefit any other auxiliary science. The same situation is with deep drilling fields. Here, we're reporting the 7 EBs that are within the deep drilling field. And then what you're seeing here are the numbers of visits. And you see that, yes, there's a little bit of variation, but at numbers that are as high as this, it means that we can actually catch not only the non-time sensitive phenomena, but also the transient phenomena. And again, while there is a bit of a difference across these OPSIM runs, they're not significant enough for us to advocate one over the other. And the last point that I want to make are the number of visits in individual passbands to be able to hone in on chromaticity. And again, I'm showing you the same thing, that effectively the 2 blue bands are not going to be all that useful, but the 4 red bands are going to be amazingly useful. And there's next to no variation across different OPSIMs. Which leads me to the conclusion. So going back to the 3 questions, is LSST going to deliver? Absolutely on the short end, but we will not be able to get long period EBs. This is probably obvious anyway, just by thinking that we're having up to 1,000 snapshots over 10 years, but still we've quantified roughly where we stand. Are passband visits adequate to provide chromatic information? Absolutely. Especially on the red side, we have plenty of bandwidth, so to speak, to get those temperatures out. And finally, do different OPSIMs produce a significant difference? They do not. We do not have any favorites across the 4 proposed OPSIMs for the 3.0. So with this, I will conclude. I will go back to this slide if anybody wants to grab any of this and play on their end. And I'd love to welcome any questions or comments or concerns or anything else that you may have.
Well, thank you very much, Andrej. That's a really conclusive result and a really interesting investigation. It's good to know what we're going to be able to learn from these. So I see there was a question in the chat already from Kelly. Kelly, could you read your question aloud, please?
Yeah, hi, Andrej, great talk. So I was just wondering, I know that in the test catalog, we have ellipsoidal variables. I assume they're included in this assessment as well. So how do you analyze whether the points are in eclipse for ellipsoidal variables, since they don't technically have eclipses, especially for the more eccentric ones?
Yes, so they are included. However, their eclipse widths are set to 0. So if I may grab the screen share one more time, there's a fine point that I only glossed over, but it may be worth stressing. Let me show this one more time. Fractions. Where are your fractions? Here. All right. So the question is, if we set our metric to 0, which means we are okay with anything above 0 points in eclipse. For example, 1 point in eclipse would already be excellent, right? Well, if you look at where 0 lands, 0 does not land at 100%, which means that you will not recover 100% of the overlapping footprint sample, no matter what you do, you are going to be losing 15% simply because those eclipses you will never hit. Those 15% in terms of the sampling that we've done is dominated by ellipsoidal variables, because the width in the catalog that's reported for those eclipses is 0, so we will never get them. And those are in this first bin. And this is, again, it's a fine point that I wasn't going to talk much about, but this is precisely the reason, and I even commented here if anybody wants to go through the details, but effectively it's the reason why we never hit 100% recoverability here.
But we will recover them. You've just specified here that we're not going to.
That's correct. For this particular metric, it's exclusively non-time critical eclipsing binaries. So the fact that those ellipsoidals are in the catalog causes this slight suppression, but it's a fool's hope to think that we are complete in ellipsoidal variables in the test catalog. I mean, ellipsoidal variables should be measured in tens of thousands, and we have maybe 200. It's just those that went through the SIFT and are binary, either from auxiliary data or evidently so. But yeah.
All right, thank you.
Thanks, Kelly. And I see a couple of questions from Kenneth Caro.
Yeah, so I just had a couple of quick questions. How does the pixel size affect this? Because in tests it's terrible. And second, how do you plan to distinguish between, say, RR Lyraes, especially the first overtone types, and these eclipsing binaries that have the same eclipse depths?
So pixel size is irrelevant for this particular use case. And the reason why is we're using tests only as a benchmark, and the fact that the eclipse depth and so on may be adversely affected by third light is really not something that goes into this metric. In other words, we know that these are eclipsing binaries, and LSST will observe these unless, of course, they're saturated because they're so bright, but LSST will observe this better than what tests will do. Your question would become much more pertinent if the sample was used from the full frame images, because their crowding really dominates your uncertainties. And the reason why that would be is because the width of the eclipse, the accuracy at which you can determine a width of the eclipse, so whether a point is in eclipse, is of course correlated with the signal to noise ratio of the light curve. And that's where you'll see that. So to your point, of course, in a real world, it absolutely makes a difference. But for this simulation, it is largely irrelevant. We just use tests as ground truth, and we don't ask ourselves what the signal to noise ratio will be. We just ask ourselves how many points in eclipse. That's it. That's because it's such a simple metric. To your second question, I would argue that this is one of the most crucial questions that we'll have to answer, because I'm here preaching how cool LSST will be, but of course, I imply here how cool it will it be after 10 years, right? Because we'll have to wait for 10 years for all these data to get accumulated. So while we can hope to get deep drilling fields much faster, and while we can hope to get short period binaries of the order of, say, half a day or something like that faster as well, ultimately, we're going to have to wait 10 years to get the true census out of it. At that point, there's going to be a massive challenge to do classification with next to no auxiliary data available, because we're on such a faint end. And then to distinguish, if somebody tells you, here, take these 900 chromatic, fortunately, but still those 900, up to 900 data points, and tell me if this is an EB or an IR Lyrae or a Cepheid or something else, that's going to be a major head scratcher. And yesterday we've heard a colloquium on that that was quite interesting. Other people will hopefully come up with grand ideas of how to handle that. My huge hope lies in Gaia to provide us with a really good benchmark once we get to DR4 or DR5. But ultimately, this is, I think, $1 million question. How do we truly infer from 900 data points once everything's said and done? So yeah, it's going to be a fun thing to do down the road.
Some work to do then. We have time for just one last comment from Peter Joachim. Go ahead, Peter.
Yeah, I just needed to count. We do have a big framework for analyzing our simulations, so it would be great to wrap this code up and drop it in just so we can automatically pipeline and as we create new simulations. And looking at your notebook, we can get you a lot faster with our framework. We can copy and paste some of your snippets in, and I think it'll just run automatically and be great.
I'm going to be as happy as a pig in a mud. The simple point is that I am a true open source believer, and everything I ever do is immediately open sourced and put out there. And here, the entire paper, even though it's still in the draft stage and I'm about to solicit suggestions, it's out there for the world to see. So every single snippet of code is, of course, up for grabs. And if I can help in any way or help clarify anything in any way, if I've done any silliness out there that I've not noticed, please let me know. But yeah, I'd love to work with you on getting that in. And I myself have never gotten proficient enough with math. I've worked with math, but I've just never gotten proficient enough with math to confidently do this. But I will also say a huge thanks to the Heising-Simons Foundation for sponsoring this, because I figured that about a month is what I need for this, and about a month is what I needed for this. So it was pretty cool.
Well, thank you, Andrej, and thanks everybody for your questions. And let me thank both Andrej and Adriano and his team for 2 fantastic talks. Really, really interesting work. And clearly there's a lot more still to do. So we will wrap it up there for today. And let me end with a reminder that we have one more colloquium later this week on December the 8th, led by Sarah Greenstreet and her team discussing orbital fitting software that they've been working on. So I hope to see everybody then. Thank you all very much. See you next time.
Bye.